Well, hello everyone and welcome to lecture 4. I think it is a good moment just to pause a little bit and see where we are in our investigations of quantum information science. I guess it's good for you to have some kind of a bird's view of the course. It's also good for me so that I don't follow my stream of consciousness and take you into some nitty-gritty details that are maybe not so relevant for the first introduction. Well, anyway, so remember we started with a notion of amplitudes. And we talk about quantum interference. So we view quantum theory as a new kind of probability theory. We calculate probabilities in a different way. And that one term that is really different is quantum interference term. It could be positive, could be negative. Probability can be a little bit larger or maybe a lot larger than in the classical case, but you can also dump them. It can be much lower, and that all depends on this interference term. So we were talking about interference. So then I took you to one qubit case. So we looked into one qubit, and that was a good example to play with quantum interference. You could see quantum interference on a single qubit. So remember this golden circuit that we were talking about, Hadamard, phase, Hadamard. So that's our single qubit interference pattern. And when we talk about some other gates, but essentially we said that you can build any quantum interference of your choice or any unitary operation of your choice with any precision at a single qubit level, essentially with Hadamard and T-gate. That was this one special phase gate that is a rotation by pi over 4 on the Bloch sphere. Then actually we also stated that if you have any number of phase gates, then Hadamard and any phase gate will do their job. So you saw quantum interference at the single qubit level, but you know, single qubit is just a single qubit, not so interesting, so we went to 2 qubit case. So we looked at 2 qubits, and that was our next step. And at this point, I introduced the concept of quantum entanglement. So entanglement entered the game here. So things are much more interesting when we have subsystems, right? So because then we can start talking about quantum interference across subsystems. And our all-time favorite gate here is control NOT gate. Sometimes we write it like this, and sometimes we write it like this, because we recognize that this gate, you know, it comes under different names. It comes as a control NOT. We call it a controlled bit flip gate. We also call it the measurement gate. And together with Hadamard, as you could see, this gate is very powerful because it can generate quantum entanglement. So it can work with the Hadamard and gives you maximally entangled states that we call the Bell states. So C0 is your favorite gate. Well, should be your favorite gate, because together with the Hadamard, it gives you entanglement. We said, well, actually, you know, Hadamard and C0 are not powerful enough to generate any complicated quantum interference, in a sense that you cannot implement any unitary operation on qubits only with the Hadamard and C0. You need T-gate. So this is actually the valuable gate. If you really want to have a set of universal gates, one choice, not the only one, but one choice is take control NOT, take the Hadamard, add one of the so-called non-Clifford gates, and T is a good choice. So having this trio, Hadamard, C0, T, you have everything. Essentially, you can just construct any unitary operation on any number of qubits with any precision of your choice. as far as precision is concerned, it's kind of easy. You don't have to work hard. The number of gates that are needed if you ask yourself, okay, what happens if I just want to have this unitary operation with slightly higher precision? Then you don't have to work that hard. You just, polylog sort of number of gates will actually do the job in terms of the number of qubits. But, sorry, in terms of precisions. But when it comes to the number of qubits, the situation is a little bit more, well, actually much more difficult. You have to have exponentially many gates in terms of, as a number of qubit grows. But anyway, C naught, Hadamard, T gates. And when it comes to one thing perhaps to mention is that the T gate is a game changer in a sense that allows you for this universality. So if you have a colleague, an experimental physicist, who's very happy and proud and says, well, look, I have an entanglement, I have a C naught gate, I have Hadamard gates in my lab, and I have a wonderful circuit composed of those gates. So that may impress physicists because you can make a very interesting source of entanglement, but it's still not good enough to impress computer scientists, because only when you have a substantial number of T gates in your system, the system is getting more and more difficult to be simulated by a classical device. Well, anyway, I'm digressing at the moment. So that was lecture 1, that was lecture 2, lecture 3, and then comes lecture 4, where at this point we identified, with quantum entanglement, we identify one problem. We said we have two subsystems, A and B, and if they are entangled, the problem is that I cannot really write the state of the whole as a tensor product of two states, one attributed to A and the other one pertaining to B. So that's not possible. So that's definition of it's a definition of an entangled state. So of course, now it begs the question: if I cannot do this, if I cannot attribute a state vector to an individual system, what can I attribute? How do I make statistical predictions? I can be in a situations where we are often in a situations, in fact, where the two entangled subsystems are miles away from each other, and so you want to do your statistical predictions here, and you don't have a state vector. You cannot attribute the state vector of your system to your system here. So what do you do? Well, how do you make those predictions? What kind of mathematical tool you need? So welcome to lecture 4. So at this point, we are going to look at these situations, and I'm going to give you a set of mathematical tools that you need to deal with the situations like this. So we'll be talking about density operators. So we'll look at the formalism of quantum theory, and we'll just introduce density operators. Remember, no matter how fancy mathematics is, it's actually not that fancy. It's finite dimensional Hilbert spaces. So most mathematicians would laugh at you, say, well, that's trivial, right? Well, it is, but the underlying physics is nothing but trivial. So remember, at the bottom of this is really addition and multiplication of probability amplitudes. All those mathematical tools, matrices and vectors, they serve one purpose. They just tabulate probability amplitudes. With density operators, we will be kind of mixing probabilities and probability amplitudes. And just as a sort of a spoiler, after lecture 4, we will go in two directions. So one direction will be, so at this point, I assume that after those 4 lectures, you have the basics, right? So you understand amplitudes, interference, you understand 1 qubit, you understand 2 qubits, you understand density operators, you can start doing calculations. But you may say, well, I have a set of tools. What is it good for? So it's good for many things, and we will talk about, so I will talk about some applications. So we will be talking about correlations that quantum entanglement can generate. So I'll talk about Bell's inequalities. And then I will talk about perhaps quantum secure, so call it quantum crypto. And so for this kind of implementations, we need just a good number of entangled qubits. But if we want to go further and talk about quantum computation, so that's going to be the next topic here. There will be just quantum. We'll talk about quantum algorithms. So that requires many more entangled qubits. But at some point, obviously, you will be asking questions. Oh, that's wonderful! You know, that's great. Quantum computers are so powerful; they can do so many wonderful things. Why don't we have them? So the answer is, well, decoherence, noise, environment. So we have to first learn what does it mean for system to interact with the environment. So we'll be talking about evolution of open systems. So open quantum system. And then I will tell you, well, it's not such, you know, a gloom and doom. It's not really that bad, because we do have some ideas and some tools to act against noise, to protect our quantum system of interest. That's a wonderful new area called quantum error correction, and also fault-tolerant computation. So that's the idea. We'll talk about things that you can understand with a set of tools that we have after the first 4 lectures, and then I will indicate a big problem with decoherence at the end of lecture 4, 5, 6, and then at lecture 7 and 8, hopefully we will try to understand whether is there anything we can do about it. So, well, let's start with density operators.